here, and I'm gonna start sharing my screen as well. Yes. Okay, so let's take a quick look here in the schedule. Okay, so today we're going to start special relativity. We weren't able to start last time, so let me adjust here. And that's going to be number 18. Okay. And well, we have to finish that today. And I'm thinking about just not covering, well, just not covering this last chapter, but the lab is still going to be due, okay? And give you some time to study for the final. That's going to be the following meeting. See, Monday is going to be our last day of the meeting. Next week, a week from now. Wednesday is a holiday. So what I'm going to do, I'm going to skip this one and make sure you turn in your lab 7 on Monday. I'll be available here online. And if you want to ask any questions, okay? And let's see.
Excuse me, Professor?
Yeah?
Sorry, isn't it lab 8? That would be due next?
Let me see. Oh, yeah, that's right, lab 8. Wait a minute. Yeah, lab 8, right? Refraction, lab 8. Yeah, that's right, that's lab 8. The last one. It was supposed to be 9. That's right, that's the last one. And let's see, let's take a look here at the chapters. That's going to be, I'm taking out chapter 28 and all labs. All chapters and labs, right? All chapters plus labs. All CPHPT. Thank you for pointing that out. And final exam, 10 a.m. to 12 p.m. Let's double check, nothing changed there in the website of the college, right? What else? LHC here. Admissions, academics, schedule and catalogs. Schedule of classes, fall class schedule. That's gonna be winter, spring. That's the one we want. Final exam, final exam date. Yeah, good question, Brianna. Let me check here. Maybe there's something wrong with my, let's see, Memorial Day. It's Monday, see that? Yeah, it's Monday. Okay, so I mixed that up in my schedule of classes. Thank you for pointing that out. Okay, so we can still cover the, let's see, P29 syllabus. Yeah, okay, so let's do it this way. 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 So let's holiday. Thank you for pointing that out, and not applicable. So, so in this case, you know, let's plan for covering chapter 29, okay? And then now you have a whole week to study for the exam. And chapter 29 again is particles and waves. Okay. This is the schedule of classes, right? Monday. Yeah, good. So you're gonna have a holiday just 2 days before the exam, Memorial Day, and 29. Yeah, right here. So we still meet on Wednesday. Final exam schedule. Okay, so they changed the table. The table used to be different. Okay, so here's an example, right? Use how you use this table, right? If your class meets on Monday only at 10:15, right? Then your final exam will be held on Monday, June 5th from 10 to 12 noon. You go 10, 10:15, and then 15 is between 10 and 12, Monday only. So that's an example, right? That's an example. So between 10 and 12 is the class meeting. Okay, so when is gonna be the exam? Okay, it's gonna be June 5th between 10 and 12, right? That's how you should read that. In our case, we're meeting Monday and Wednesday between 7:30 and 9:30. Okay, so that's the starting time of the class. We start at 8:50. So our final is gonna be May 31st from 7:30 to 9:30. Okay, let's make sure everything is right here. Let's see. It's 7:30 to 9:30, huh? Let's make sure everything is right. Let's see. Monday and Wednesday. Classes start at oh, they excluded 8:50. Okay, so it must be this one. It must be this one. See, classes that start at 10:15 and 10:35 a.m. Okay, so a.m. class that start at 8:50. So that's gonna be this one. May 31st from 10 a.m. to 12 noon. So the date there is correct. 10 a.m. to 12 noon. 31st. And I'm going to boldface that. Now, chapters and labs. Final exam. 10 to 12, 10 a.m. to 12. And labs. One more student joining us. So that's the situation. Okay, so we fixed everything here, right? There's no other mistake here. And anything else that you might pick up that I didn't? Let's see, this one here is a holiday. Yeah, I'm gonna put that in bold-faced and italicized. And okay, now we're going to talk about the physics of the 20th century. Special relativity is the physics of the 20th century. So the main guy behind that, it's amazing that he managed to do that, is Albert Einstein, right? he saw what no other person was able to see behind this contribution and others was Albert Einstein. It was no minor feat what he managed to do. Einstein. The idea he came up with was completely out of the box. Okay, that's why I said nobody was able to see that, and it passed a long time until his theory, this theory and the other, not only special relativity but of general relativity, it passed a long time until those two theories were accepted by the scientific community. It was so out of the box, but so out of the box, it was proposing so many ideas and consequences that are almost unacceptable that it took quite a long time for the community to accept this theory. So much that when Einstein received the Nobel Prize in physics, it was not the special relativity and the general relativity was not mentioned specifically. He actually got the Nobel Prize for other contributions. Okay, he got the Nobel Prize for the explanation of the photoelectric effect. Yeah, that was mentioned specifically. He got the Nobel Prize for the Brownian motion of the molecules. That was mentioned specifically. But then the Nobel Prize committee stopped there and said, and other contributions. They didn't mention special relativity and general relativity as the other contribution, even though, it was worth a Nobel Prize, maybe two. Okay, not just one Nobel Prize, maybe two. And the idea was so out of this box, and he managed to prove that just because experimental evidence was being observed to corroborate his special relativity and the generalized relativity. Today, we use generalized relativity to program our GPS satellites that are there in space and transmitting signals to our GPS receiver. So the GPS device that we use today, it was possible only with not just a special relativity, but general relativity as well, which is more complicated than the special relativity, but the ideas are quite similar. Okay, and so let me introduce you before we go into that. Let me just remind you of the laws of physics. Laws of physics. Laws of physics so far that we study Newtonian mechanics. Newtonian mechanics, I introduced to you 4 laws of physics. Actually, 3 laws of physics, okay? But let's just say 3 laws of motion plus the law of gravitation. Don't forget, it's not exactly 3 laws of motion, but in reality it's only 2, because one of them is dependent of the other. In reality, it's just 2. Second law of motion and the third law of motion. The first law is just a special, it's just a consequence of the second law. Remember, the laws are the starting point, okay, of any theory. Of course, the laws together with those basic quantities. So in Newtonian mechanics, in thermodynamics, we also have 4 laws. Thermodynamics. 4 laws. The zeroth law, the zeroth, first, second, and third laws. Then we look into E&M. E&M, we have 4 laws again that we study, right? Choose laws of the magnetic field, 2 Gauss law. Gauss law, let's see. Gauss's law for the electric and magnetic fields. Ampere's law, and Faraday's law. Then in ray optics, we have the law of the least time that I discussed here with you as well. Optics. And now in relativity, special relativity, Einstein was very specific about naming it the law of special relativity. And later on, he developed what we today call, Einstein developed the law of general relativity. It is special because it's, they also call it, they also call restricted special relativity. They also, some countries call it the law of restricted relativity, something like that. But let's use the other concept, okay? Why is it restricted? Okay, there's a reason why some people call it the law of restricted, special relativity restricted, but let's use it special. Okay, there's an important difference between this law and this law here. We are not going to study general relativity, okay? The law of special relativity, we call it special relativity instead of general relativity, for a good reason. Because this law applies only to inertial referentials. Okay, applies only to inertial referentials. On the other hand, the law of general relativity applies. And what do we mean by, first, what we mean by inertial referentials? Inertial referentials mean referentials that are moving with constant velocity, okay? So when Einstein finished his theory of special relativity, which he published, okay, some people argue that there was, some people claim that there was no peer review on his papers. He called it special relativity because, in this case, he made the assumption that this law applies only to referentials that move with constant velocity. In the case of general relativity, the referential could be accelerated. Okay, that's why it's called special relativity. And he proposed 2 postulates or laws. Postulates, you have to memorize them, right? If there is anything in physics that you have to memorize for the rest of your life, are the laws of physics and the basic quantities and the basic definitions. That's what you have to memorize for the rest of your life. Everything else you can derive mathematically. So what's the first postulate? Just go back to your book, okay? Or any book in special relativity, and you're going to see it's not that difficult to understand, okay? not that difficult to understand this law. The trick is to understand the second law. The second law that the one that people couldn't accept easily, the one that took a long time for Einstein's peer to accept. Okay. Okay, the first one is called the relativity postulate. Okay, and what does it state? The laws of physics are the same in every inertial reference frame. If you don't remember, I'm going to mention what the inertial frame is. Okay, inertial frame of reference is. And why is it relativity too? There's a reason why we call it relativity. Okay. We call it relativity because it refers to relative motion. Okay, let's write that down. This theory is called relativity. Let's put between quotes, because it refers to relative motion of objects between each other. And remember, some people call it restricted, right? Postulate of restricted relativity is restricted because it refers to only inertial reference frame. The second one is a little bit more difficult to grasp. No, not is that difficult to grasp, it's difficult to accept. The law, the speed of light law postulate. The speed of light postulate. And what does the speed of light postulate state? Okay? The speed of light in a vacuum measured with respect to any, and I'm going to boldface it and italicize, any inertial frame of reference always has the same value of c, which is 300,000 kilometers per second. Okay, no matter how fast the source of light and the object and the observer are moving relative to each other. See the word relative here? And I'm gonna give you some examples, okay? I gonna get here, okay, illustration of relativity second postulate. But before I go to relativity second postulate, let's think in terms of inertial frames of reference, okay? So suppose that you're in the ground, standing on the ground, and you go ahead and you create your reference frame. Your reference frame is gonna have a y-axis and an x-axis, okay? And that's my y-axis, that's in the vertical, and the x-axis. You can do that. You're standing on the street, okay, and you go ahead, you visualize this x and y-axis, and even x, y, and z too, because we live in a three-dimensional world, right? And that's gonna be your referential. If this referential of yours is not accelerated, if you cannot measure or feel any acceleration whatsoever, you can consider this referential a inertial one. So referential A is an inertial frame of reference. And then a car passes by, and that car not passes by, but is moving towards you. A car is moving towards you, and that car is also moving with a constant velocity. And remember, it's moving with constant velocity. It cannot change direction and cannot change speed either. That car is also considered an inertial referential. And that's how I label my second inertial referential as B. Okay? So now we have two inertial referentials here. They're both moving with constant velocity. According to you, your referential is at rest. But that's where comes the interesting picture, right? Interesting fact. But according to this referential, according to the car, he is the one who is at rest, and you are the one that's moving towards him, okay? That's the idea. Okay. So theory of relativity makes use of this idea that inertial referential. So let's write that down here. Theory of relativity makes use of this idea of inertial referential. Okay, if the referential is accelerated, then the theory of relativity doesn't apply. Special relativity does not apply. Instead, you have to use the theory of general relativity. Okay, so the idea of referential frame was explained. Let's go to the next idea, right? To the next postulate. Assume that you are there standing in the street, okay, your referential is A, and you have a laser pointer. You're not moving, you're attached to this referential, and then far away you place a detector that is also at rest. A detector that's at rest with respect to the ground. Okay? You go ahead, shine the laser in this detector. There are detectors that allows you to measure the speed of the light, by the way. And what this detector is going to measure? This detector is going to measure 300,000 kilometers per second. That was Einstein's second postulate states. But Einstein's second postulate states more. He also states that if your detector is now moving toward your laser source inside the car, right? Inside that original car, you point the laser towards the detector and you measure the speed of light. What the detector is going to find out? It's going to find out that the speed of the light is still 300,000 kilometers per second. No matter how sensitive your detector is, he is not going to give a result of 300,000 kilometers per second plus VBA. Okay, that's a basic divergence between special relativity and Newtonian physics. In Newtonian physics, this light would be thought to be moving at 300,000 kilometers per second plus the velocity of the detector moving towards you. Remember, this guy is attached to the referential B. Okay, so that's how we illustrate the second postulate. You can do the other way too. Instead of having the detector moving towards you, you can also have the detector moving away from you. Newtonian mechanics would state that the velocity that your detector would be moving would be 300,000 kilometers per second minus the velocity of the frame of reference. Let's say 30 meters per second, for instance. But that's not what we get in nature, in real life. In real life, we get the detector still measure the speed as being 300,000 kilometers per second. Again, that's the second postulate of Einstein. And it doesn't matter how you do it. Whether the detector is moving towards you, away from you, or if the detector is at rest and you are moving towards the detector or away from you, from it. Did you get the idea? Okay. So we can summarize this idea right in here. The second postulate can be illustrated in the following way. Illustrated in the following way. If you have a laser pen and a detector to measure the speed of light. One, if the detector is at rest with respect to the laser pointer or the laser pen, right? Nowadays we sell those things at very cheap price, right? $30, you can buy one of those laser pointers. Even less up to, if it depends on the place that you go. If the detector is at rest with respect to the laser pointer, the detector will measure a speed of 300,000 kilometers per second for the laser light. Likewise, if the detector is at rest and the laser pointer, if the detector is at rest, now let's see, if the detector, no, instead of that, let's put it this way. If the detector is moving towards the laser pointer, the detector will still measure as a speed of 300,000 kilometers per second for the laser light. Okay, if the detector is moving away, right? That's what those drawings mean. Away from the laser pointer, the detector still will measure a speed of 300,000 kilometers per second. Two more other cases, right? If the detector is at rest, right? Is at rest. And the laser pointer instead, pointer is moving towards the detector, comma, the detector still will measure a speed of 300,000 kilometers per second for the laser light. And finally, the last one, right? Laser pointer moving away from the detector. So all those 5 situations, and that's the idea that you must believe. Okay, that's the idea, because Einstein's contemporary didn't believe that. They didn't believe why? They didn't believe because this second postulate had very strange consequences that they could not believe. Not because of the postulate, but because of the consequences of the postulate. And we're going to study those consequences, okay? Because that's when we come to the light clock. A light clock. The second postulate, although seemingly simple, has very important consequences. I'm going to just mention what the consequences are, and then I'm going to prove that to yourself. Okay, I'm going to prove that to you. Not all of them, but some of them. Okay. The first thing is that depending on the speed, very important consequence. Some of them being one, we have this phenomenon called time dilation. Okay. What does it mean, time dilation? It means that clocks are observed, time, not clocks, but time is observed to flow differently between inertial frames of reference. I'm going to give you an example. Okay. Time dilation, that's one consequence. Another consequence is length contraction. The length of an object, let's not use the flow different. Time is observed. Yeah, good. Time is observed to flow differently between inertial frames of reference. Let me elaborate a little more here. In other words, a clock in an inertial frame of reference will flow is lower than, let me see, a clock in your frame of reference, better, in your inertial frame of reference flows faster than another clock attached to a second inertial frame of reference that is moving. That's a very important consequence. So if you have two inertial frames of reference, you and someone else, the astronaut that is in his spaceship, okay? If they observe the period of motion there is around the sun, they're going to find different translational times for that. Okay? That's what happens. Length contraction is not difficult to understand. Length contraction is that if you're on Earth, okay, the length of an object is measured, not seen, is measured to be shorter. The length of an object in a second inertial frame of reference is measured to be shorter. That's why it's called length contraction. Okay. And then there's more. Okay. The linear momentum must be rewritten to be conserved. Okay. We're going to cover that. The relativistic, right? The relativistic linear momentum must be rewritten to be conserved. your regular linear momentum, P equal to mv, does not conserve from one inertial frame of reference to another. And I'm going to write it down. What's the relation that applies for conservation? We have that relative velocities are also slightly different. And finally, we have that the phenomenon of relativistic energy, which is illustrated by that famous Einstein equation, E equal mc squared. This is a consequence of Einstein's second postulate as well. Remember, what you see here is not a law, it's a consequence, okay? Okay, someone else is coming. Let's see, who is that? Justena, here you go. 9:32. So let's see how we can get all that stuff, right? We start, in order to prove time dilation, we have to create a special type of clock. Special type of clock that we call the light clock. Okay, remember, light travels with constant velocity, right? From light has the same speed, right? Even better, light have the same speed from one referential to another. Whether has the same speed, whether it is in referential A or referential B. A or referential B. And then we go ahead and gonna use the light clock here. And how does the light clock works? The light clock, the idea of the light clock is very simple. Okay, we have, here you go, here's the light clock. This light clock is made of two mirrors. Try to picture that in your mind, how it works. It's made of two mirrors. And then you go ahead and insert a photon of light here somehow. And this photon of light is gonna tick and tock between those two mirrors. Tick, tock, okay? That's the light, that's the idea of the light clock. We have a very nice video about that mechanical universe that illustrates this idea of the light clock, See, Lorentz transformation. Let's try this one here. Mechanical universe. Unfortunately, those, oh no, wait a minute, velocity and time, the mechanical universe, special relativity, here you go. Let's try this one. This one definitely has the light clock in there. And unfortunately, the quality of this video is not good, you know. I used to play a video with a much better quality there at Santa Monica College. But all I want to do, I want to adapt it for school use. I want to show you the light clock.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point.
Okay, here you go. We don't want that. We want this one here. Here you go, I got it. The light clock.
Simplest.
Here you go. That's the light clock. Here you go. Here's Einstein, right? And he's holding his light clock. One mirror here, another mirror there. And suppose that somehow we were able to build a light clock like that with the photon of light bouncing back and forth, right?
Consider the simplest possible clock. Two mirrors a fixed distance apart, with a light pulse bouncing back and forth between them, shown here as a dot. Each bounce of the pulse is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary.
That's the distance that the light beam travels in Henry's clock, right? C times delta t prime. It's calling delta t prime the velocity of the light. Henry's going to see the velocity of the light as being t, right? As being c, but he's going to measure an amount of time, delta t prime, between this point and this other point.
But for Albert, that clock is moving. And between tick and tock.
And that's exactly how Einstein sees the motion of this clock, right? He doesn't see delta t prime, which would be the d, the distance. He sees the light traveling a larger path, okay, which is going to be the hypotenuse of a right angle triangle here. Okay, hypotenuse here, side, this side is going to be the length of the clock, I call it d, and this distance here is going to be the velocity of the referential frame times delta t, which is the amount of time that Einstein measured. Okay, if this clock is transported to Einstein's referential, he's going to see the clock moving in a straight line in the vertical direction. So even though Einstein's clock, and this guy is Lorentz, right? And Lorentz clock has the same length, both clocks, they are going to measure a different amount of time because of the motion, because of the relative motion, okay? That's the idea of the light clock, and we're going to derive what's going to be the difference in amount of time between one referential to the other, okay? And oh, let's do that. He's going to show that to you, and I will document in my notes as well. Here you go.
He sees the light pulse trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers. So the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
Here you go.
The relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors by the factor 1 over the square root of 1 minus v squared over c squared.
Okay, so this term here that you see, we call it gamma. It appears very frequently in relativity. 1 divided by the square root of 1 minus v squared over c squared. C squared is the speed of the light. Okay. So
this factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
and here how gamma behaves in the graph. Gamma versus v. As v increases, gamma becomes larger and larger, but gamma becomes larger and larger only for very high speeds, very close to the speed of the light. Okay, and diverges all the way to infinity at v equal to c.
So to an observer at rest,
So that's what Einstein sees for this clock. If he can visualize this other clock that's moving is going to measure that this clock is moving slower than his, no matter how similar those two clocks are. That's a very important consequence of that second postulate of Einstein.
Just a moving light clock seems to be running too slowly by the factor gamma. A ruler or anything else in motion.
Here's another consequence. You know, a ruler of same lengths when they're in the same referential, right? Whenever they're not moving, one ruler is gonna seem to be shorter than the other.
So seems contracted by that same factor.
Notice that Lawrence, this guy is Lawrence, okay? And he seems to be slimmer too, right? Because he's also contracted, but he's contracted only along the direction of motion. Only along the direction of motion.
And it's called the Lorentz contraction. See?
This contraction was, by the way, discovered by two scientists before Einstein himself, Lorentz and another guy called Fitzgerald. It's a very interesting story, okay? Even before Einstein, they start to get a glimpse of how relativity, what would be the consequences of relativity. They didn't quite have in their mind what was happening, right? They just observed some experimental results. They just look at some experimental results and start to wonder if the experimental result is right, what would be an explanation for this result.
These strange effects of relativity can be visualized using a space-time diagram.
Okay, we're not going to get to the space-time diagram. It's too much. No, it's too much. Okay, so let's document here. I'm going to show my light clock here. Here you go. Here's the length of the light clock. Here's my two observers. One is Einstein, right? And the other, Einstein's this guy here that rests with respect to us. And this other guy here is Lorentz. Okay, he's moving. Okay. Lorentz, see the light, the pulse of light moving up and down. The pulse of light of this clock moving up and down, right? But Einstein, right? Let's move it a little bit more. But Einstein see this pulse of light moving in a different way. Moving in different way. In this way. Okay? So you are at rest with respect to the clock. You see the motion of the light beam up and down in the vertical direction. But if you look at the same clock in another referential, it can be an airplane, it can be a car, it can be a rocket. Okay, you're not going to see the same path. You're going to see a longer path. Okay, and let's take a look here. My notation is slightly different from the video. Okay. Okay. So what does the notation means, right? When I start with this one here. Okay, the period of the clock C with respect to referential B. The clock is in referential B. So it's going to be twice D because the clock goes back and forth, right? Divided by time C. There in the video, they didn't call it CD, they call it V delta T prime. I'm having a problem here with my Word document. See what's going on here. Yeah, see, it's not cooperating. Ah, man, I hate that. stuck. Well, it's 9:46, right? Let us take a little break, and then until then, I will figure out what's the problem, okay? Until that's today is the 22nd. Randy, are you there? Randy, I think I saw Randy here, but I don't see him. Okay. 0. Vanessa Bonilla, are you there? Hello, Vanessa. Okay, I'm gonna give a little star for Vanessa. Ashley Diaz, are you there? Ashley? Ashley is not here. Natalie Espinosa. Thank you, Natalie. Janet Garcia. Thank you, Janet. Noor. Thank you, Noor. Next is Blanca Hernandez. Oh, Blanca. Kaylee Hernandez. I don't see Kaylee. Okay, next is Joshua Jimenez. Joshua Jimenez is not here either. Alondra Lima. Hi, Alondra. Thank you. Kennedy. Kennedy is here, right?
Hello, Professor.
Thank you. Okay, Randy just joining us, right? Let me get Randy in. Where is Randy? Randy Bautista. Hi, Randy, are you there?
Yes, sir.
Thank you. Vanessa, are you there, Vanessa? Okay, good, thank you. Okay, and Ashley is not here. Kaylee is not here. Joshua, I don't see him either. Okay, next is Daisy Mariscal. Thank you, Daisy. Yesenia Montes Rodriguez. Thank you, Yesenia. Ryan Ong. Hello. Good, thank you, Ryan. Artur Pacheco. Thank you, Levilud. Levilud doesn't seem to be here. Yeah, okay. Next is Donia.
Here.
Thank you, Donia. Elika. Artur Pacheco is here. Yeah. Elika Bate. I don't see Elika. Next, Brianna Valencia. Good, thank you, Brianna. And Justena Youssef. Okay, so we have how many students? 15. Okay, good. Everybody's here and the numbers match. Let's have our break and I'll figure out what's happening to my Word document. Most likely was those equations that I inserted in there and it's giving me trouble. Okay, good. Okay, now it shouldn't misbehave anymore. And I'll pick up on that. Okay, so break from 9:50 to 10 a.m. Yeah, it's too slow. Huh? I'll have to erase altogether. Yeah. And then just type it from scratch. Okay, so I see you in 10 minutes. Okay, I'm back here and So let's I want to use the notation of the book. Okay, so it's easier for you to cross-check with the book. Okay. Okay. Okay, so the notation of the book is similar to mine. Okay, so let's use what I did here, right? So the lengths. The lengths. Oh, okay. The lengths of the clock. Length. Oh man. Length. Oh gosh. Of the clock is D. Okay. The height. Let's see the height, right? The height. Yeah. Looks like I have to enter another document here. So otherwise it's gonna be let me start from. So I'll have to post two documents, okay? From now on I have to post two documents there for the notes. But this one for some reason is slowing me down. I do not know if it's something I pick up from the PowerPoint or if it's just the document is too big. Let's see. Yeah, it looks like the document is already too big. Oh, by the way, I forgot to tell you, section of the chapter 26, chapter 26, right? We didn't do 26.4, so you can strike that out. Okay, just a reminder here, I forgot to tell you at the beginning. Now let's get another document from scratch. This one here, let's see. Okay, this one's behaving better. Okay, so okay, now it's gonna be P07 notes 1. Okay, good. So height of the clock is the speed of light, c. Speed of light, c. Okay. The speed of referential b, right? Which is the referential that are passing by you. Referential b, moving referential. E. Okay, so here you go. Referential A, your referential. Your referential. So both referentials have exactly the same light clock, have exactly the same light clock. Okay. In referential A, the amount, the period, okay, the period of your own light clock is, okay. So here goes D, right? The length of the clock is equal to C. Well, don't forget it's back and forth, right? So because it goes back and forth, it's going to be C delta T. Okay. In the video, you just did calculate this thing for a one-way trip, right? But it's a round trip. The light beam is going back and forth, so it's is covering twice the distance, right? Twice of the distance gives you the period of that light clock, and the period of the light clock in your referential is the period of your light clock, right? In your own referential is going to be 2D divided by C. That's the period. Okay. But now the period, okay, the period of your online clock. Now, when you observe the clock, the moving clock, right? The moving clock in referential B, shall be, you find a different period for this clock. And this period is going to be what? It's going to be, it's not going to be D, it's going to be that hypotenuse that you saw, right? It's going to be, you know, I'm gonna put parentheses here. D squared plus V delta T twice D, should be 4 here because it's round trip. 4D square, let's see. Yeah. 4D square plus V delta T over, okay, V delta T, yeah, the round trip, we gotta be able to make it square because it is the hypotenuse of the triangle. Okay. And here we must have also C square. C square delta T square. Okay. And don't forget, that's the amount of time that you measure from your own referential. From your own referential. And now we're going to take like that, right? I'm going to square those two terms. Those two terms, and then the next step, I'm going to pass this term to the other side. Don't forget, I'm measuring the period of that clock that's moving. And then what else I'm going to do? I'm going to factor those two terms. The nice thing about relativity is that a pretty good amount of relativity can be dealt just with algebra. You don't require calculus. Not everything, but most of it requires just a, algebra. And now what else I'm going to do? I'm going to do a little trick here. I'm going to factor C outside this parenthesis. And when I do that, I must have c squared right in here. That's what you saw in that video, okay? What I'm doing here is exactly what you saw in that video. And good, so now we have this equation. Do you see 1 minus v squared here, the gamma factor? We are almost there. Okay, c is gonna go to the other side. Oops. And by the way, instead of calling this one here delta t, let's call this one delta t naught, okay, which is a better notation. There's a reason for that. That's the period that delta t naught, you know, the above period is the period that you observe for in your own clock, and the period that the astronaut observes in his own clock. These periods are the same because they are looking at clocks that are at rest with respect to them, okay? These two periods must be the same because each observer, right? The you and the astronaut, you on the ground, and the astronaut in his spaceship are measuring the period of the same clock that are at rest with respect to you and the astronaut, okay? That's why it ends up being the same period. The difference arises when you look at the period of the clock of the astronaut. That's where the difference arises. Okay, and we are going to take the square root now. I'll put my delta t here. Delta t here, and I'm gonna put my square root right here. And what you see right in here is gonna be what? It's gonna be 2d, capital D, over c. Okay. And by the way, going back to d over c, we can here write that as delta t naught. And this factor here that you see, we call it gamma delta t naught. Now we can come up with some nice examples, right? Let's look at an example here. Okay, example. Okay, if This delta T naught, we call it the proper time, okay? And let me delta T naught. Delta T naught is called the proper time. Again, I'm going to repeat. What's the proper time? What is the proper time? Is the time that you measure with the clock at rest with respect to you. Okay, if you have a clock that's at rest with you, with respect to you, call it delta T naught. If the astronaut has a clock that is at rest with respect to him, he also called the same amount of time, that was delta T naught. Okay. Example. Let the proper time be 1 second. You see a clock moving past you with a speed of let the measured proper time be 1 second. You see a clock moving past you with a speed, I'll put it 0.3 meters per second, okay? Which is a transonic speed, the speed of sound. Okay. What is let's see, you see a clock moving past you with a speed of 0.3 meters per second, right? If your clock that is at rest with respect to you measures an amount of 1 second, how many seconds would the other clock indicate? Okay, that's a solution. Okay, so the equation you have to use is this one here. Right this one here. You go ahead, have 1 second here, and then you have to, it's not 0.3 meters per second, it's 0.3 kilometers per second, okay? Now you gotta substitute everything here, 0.3 kilometers per second, you square it, and then you go ahead and you put 300 to 3,000 kilometers per second, comma here. And look what you're going to get in this case, even for transonic speeds. Even for transonic speed, I'm gonna go to my software to crunch those numbers. I can also use Excel or my calculator. Okay, so he goes delta T is equal to 1 times second square root parenthesis 1 divided by 1 minus divided by 1, put the parentheses here, minus 0.3 kilometers per second square divided, and then I have to put divided. Now it's not going to be 0.3, it's going to be far more. And let's not forget that we're still squaring a large number, right? 1, 2, 1, 2, 3. Okay? Look what happens. Even for transonic speed, which is pretty fast. Okay, I'm going to expand. Okay, you can see that this value here is so small, but so small that it's almost 0. Okay, so small that my software is indicating 1 divided by 1, right? This, we can even try to do it separately to have an idea. I'm going to do it in the following way: 0.3 kilometers per second. And then instead of squaring, initially square, I'm going to divide them initially, and then I will square. Okay? So you go. That's what I'm going to do. Let's see what we get. Expand. See, 10 to minus 6 is a very small number. And then I square 10 to minus 6. I'm going to get what? 10 to minus 12. Okay? The difference, that's what I'm going to put it right in here. Let's see. I'm going to get like that. So by doing this way, I was able to find out the exact value, right, of that ratio that you see. And now I can place it here. What did he do? What a shame. Okay, 10 to minus 12. I'm going to erase this one here. And, okay, I'm going to 10 to minus 12. I'm going to go like that. 10 to minus 12. Okay, and you know, because this number here is so small compared to 1, what is it going to do? It's going to say that, let's see, expand. Yeah, it's going to say that's 1, right? Almost, but in reality, it's not exactly 1. It's 1, you know, 0.000 whatever. Okay, this number here is going to be slightly more than 1. See if I can get the exact number with this guy. Yeah, he doesn't cooperate. He's still doing, unless I increase the resolution of the software. But you know, at this speed, what's the result here? The result here is that this number is so small. I'm going to finish here. 10 to minus 12. 10 to minus 12. Oops. Here you go. That we can hardly measure the difference. Okay, a good approximation for that would be something like that instead of doing the square root. Okay, a good approximation for that. I'm going to even put approximation here so you can have an idea. Here goes. This one would be 1. This is the binomial approximation. 1 minus half 10 to minus 12. Okay. So we have oh, it's not minus, it has to be plus here. That's the binomial approximation. And you have this half here because of the square root. So this half comes from the square root. So it's slightly more than 1 second. But the number is so small that my software there is not picking up on that difference, okay? But that's the case in which the clock is moving at the speed of the sound. What if it starts to move at the higher speeds? Okay, instead of 0.3 kilometers per second. What if the clock starts to move at, let's say, 0.1 C? Okay, 0.1 C is 30,000 kilometers per second. And now what I'm gonna do, I'm gonna have 0.1 here, 0.1 C here, divided by C. And on the top of that, I will have to, I'll have to square it. Okay. When we do this math, the C is gonna cancel out with the C. Right? And we have to square the 0.1. When we square the 0.1, we get 0.01. 0.01. And now we start to get some values that we can start to visualize what's the effect of speed in the time that we measure in the clock that's moving. Okay? Here, what we end up getting is going to be 0.99. 0.99. And now you can divide 1 by 0.99. One divided by 0.99. Take the square root. I get 1.005. It's still a very small difference, but that's because I'm going just a tenth of the speed of the light, 0.0050 seconds. That's what you measure for. That's what you measure in that 1 second of proper time for the motion of the other clock. Okay, so the other clock is going slower according to your clock, because the second clock is moving slower with respect to your clock. Okay. In other words, your clock indicates 1 second for its own period, right? Whereas the same amount of time is measured as being 1.005 seconds using the second clock. Okay, now let's go another step. Okay, instead of 0.1 C, let's do that for 0.5 C. 0.5 C. And then we're gonna get 0.5 here. That's gonna be 0.5 here. That's gonna be 0.25 here. 0.75 here. And then you do the math, right? You do the math. 1 divided by 0.75. 1 divided by is the square root of 1 divided by 0.75. It is 1.15. 1.155. Now we start to get a difference of 15% between your clock and the other one because of the speed of the light, because of the speed of the rocket. That's what we call the time dilation. That's what we call time dilation. So the numerical examples, and the faster it goes, right? If the guy approaches the speed of the light, then you're going to have 1 divided by 0 here. right? If your second clock is moving at the speed of the light, you're going to have 1 divided by 0 here. It is as though as the other clock is not moving at all. This is as though the other clock is standing still. Okay? If as you know, the speed of the second clock approaches c, comma, it is as though approach c, comma, its period tends to go to infinity. What does it mean? The second clock isn't moving at all. The second clock does not move at all. Okay, that's the effect of time dilation. And by the way, this phenomenon has been extensively documented with experiments. Okay, and what are those experiments that we have done? Your book discussed that. One of them is a clock that is placed inside an airplane and flown around the world. An atomic clock. It's an atomic clock. Inside an airplane and flown around the world. Leaving behind an exact copy of the same clock that stays on the ground. When the second clock returns, there is a very small time difference between them. Okay, that's one. And there's a paper out there that documents that. Okay, there is another one. Is the lifetime of the muon, lifetime of the muon, which is a particle that enters the Earth's atmosphere at, we call it relativistic speed, relativistic speeds. Okay, it has been possible. It has been possible to observe that a muon that enters Earth's atmosphere at relativistic speeds, lives longer than a muon that is at rest in the lab. So those are the two experimental evidences that we see out there. That's time dilation. Now let's talk about the length contraction. Okay. The way we explain length contraction is the following. See here if I have one good one. Okay, so I don't. It doesn't look like I have one here. Let's see. Okay, right here. Okay, so here you go. Here, one planet. And here's the second planet. My planets are not exactly spherical for a very good reason, okay? The distance between those two planets is L, okay? And you know that this spaceship is moving at a given velocity, relativistic velocity, okay? Can you picture that? According to your referential, this spaceship is going to move at distance L divided, is going to take an amount of time L divided by VBA, okay? Consider now lens contraction, right? Going back here. Consider two planets separated by a distance L and a spaceship moving at a speed v. Okay, this spaceship is flying from the first planet to the second, from the first planet to the second. For you who stayed behind, okay, you measure the length of the trip as being what? Let's not forget that the speed of the spaceship is v, right? The distance is L, and the amount of time that you're going to measure, though, for you who is staying on Earth, is going to be delta t. And let's italicize that to look better. So that's the amount of time that you measure, okay? But let's not forget that the clock in the spaceship is going to measure a different amount of time. And the clock in the spaceship, I'm going to call it delta t prime, because it's flying faster, right? It's going to measure, square root 1 minus v squared over c squared. Okay, over delta t times delta t. Times delta t. That's the idea of the length contraction. Delta t prime is how much the astronaut inside the spaceship measured the length. Okay? But the astronaut also knows that he's flying at the same speed that the other observer is measuring. The astronaut knows that, he's gonna is flying at the same speed of v, right? Same speed v. But there is one more thing. In order for delta t prime be the same as delta t times this value here, right? We must have a different length that the astronaut in the spaceship measured. Okay? And that's why I'm putting the prime here. And having that in mind, we can prove the phenomenon of length contraction here, which is going to be L prime equal to V, equal to V L prime equal to V square root 1 minus V squared times delta t. Okay, but let's see. I'm going to put this V here next to the delta t, right? V delta t is nothing but the L that you measure while you are in the planet, but the astronaut is not measuring L. The astronaut is measuring L times the square root that you see here, okay? Which, by the way, becomes 1 divided by gamma. If you have gamma times something in the first one, in this one you have divided by gamma. Okay? Remember, this number is going to be less than 1, right? And 1 divided by gamma is going to be less than 1 as well. Sometimes it's a little bit confusing, you know, defining gamma this way. So let's keep it this way. Okay? So that's the length contract that we're talking about. The astronaut measure a distance from one planet to another as being shorter than you that you're measuring, than you that is at rest with respect to the other planets. Okay? For you who stayed behind in the first planet, which is at rest with respect to the second planet. Okay? For you who stayed behind in planet A, I'm going to put this way, planet A, which at rest with respect to planet B, you see the distance from A to B as being L. However, for the astronaut in the spaceship, he measures, not sees, but measures. I don't like sees. You measure, right? However, for the astronaut in the spaceship, he measures a distance L prime, which is less than L by a factor 1 divided by gamma. And then you can do the same thing that we did for the delta t, right? Plugging numbers in there to find out by how much that the length decrease, okay? Note that the gamma factor starts to be, you know, appreciable only for very high speeds. Okay, we saw that we got what, a 15% difference for moving at half the speed of the light, right? That's why we don't observe this type of relativistic effects in our day-to-day life. We need to go elsewhere. We need to go to the laboratory. We need to observe the nuclear particles moving, because those nuclear particles, they move at very fast speed. We also have to go to the center of the galaxies, where stars moves at relativistic speed around the center of the galaxy, where we have a supermassive black hole. But in our day-to-day life, we don't observe that. But it is important when you go to the lab, and also when you have those GPS satellites out there too. Okay. orbiting the Earth. The difference becomes appreciable in those cases, especially if you want very high accuracy in your measurement of the position using the satellite, using the GPS satellite. That's, 28.1, we did 28.1, 28.2, 28.3, and so far 28.4. Events, the postulates. 21 is events in inertial frames of reference, okay? The definition of inertial frame of reference, again, is a referential frame that's moving with constant velocity. In 28.2, we have the postulates of special relativity, that we have two postulates. 28.3 is time contraction, time dilation. And 28.4 is length contraction. And then we have also 28.5, that's relativistic momentum. Okay, let's talk about relativistic momentum before we go into our break. Relativistic momentum. Okay? Remember from physics 7? From physics 7, we have that the regular momentum is given by P equal mv. Okay. And we know, when n, if the net force applied to an object is 0, right? Not an object, but to a system, right? To a system. A system can be more than one object, is 0. We know that this quantity is conserved, right? Initial momentum, in other words, initial momentum is equal to final momentum. Okay, so when we apply this definition of momentum to relativistic situations, okay, we discover two things. One, the momentum measured in referential A is the numerical value, right? Numerical value of the momentum measured in referential A is different. Is different from the numerical value of in referential B. What else do we know? See? And 2, that momentum may be conserved in referential A, but is not conserved in referential B. That's what we observe. Okay? Referential B is your proper referential. So in order to fix the situation, in order to fix this problem, what do I mean? In order to ensure that momentum is conserved in both referentials, they still can be different from one referential to another. Referential, we have to redefine this quantity, okay? And what Einstein found is that the relativistic moment is slightly different than the one that we defined in physics 07. Okay? He found that if momentum is to be conserved in both referentials, we have to rewrite this equation like that. 1 m divided by something else, okay? And what is this something else? This something else must be a unitless quantity, okay? It happens that this something else is related to our old gamma factor, okay? Which, by the way, it's gamma. So this is more like of a guessing than a derivation, okay? If we use this relation for the relativistic momentum, we may find out that the values of momentum in referential A is different from the numerical value of the momentum in referential B. Yes, we do find that out. However, there is conservation of momentum in both referentials, okay? If we use this relation, we find the following. 1, the numerical value of momentum of the relativistic momentum measured in referential A is still different from the numerical value measured in referential B. But in this specific case, momentum is conserved not just in referential B, A, in both referentials A and B. Okay, that's what you have to know. And by the way, this term that we see right in here, this term that you see right in here, some people call it the relativistic mass, okay? The term in boldface is usually referred to as the relativistic mass, implying that mass increases as it moves faster and faster, okay? Implying, and that's exactly what would happen. You have a number that's less than 1 here, right? And as v increase, 1 divided by a number that's less than 1 is more than 1. And as v increase, the number becomes smaller and smaller. Consequently, 1 divided by that is going to become greater and greater. Okay? M, the parameter M is referred to as the rest mass. The mass, in other words, the mass of the particle when it is, or the object, right, when it is at rest. Okay, so let's okay, so what we have those phenomena of 1, time dilation, 2, length contraction, and 3, how do we call it? The mass increases, right? Increases. So if you see a particle flying by in front of you, you are going to measure a mass that's larger. In other words, if you see a particle flying by you, comma, you will measure a larger mass. However, someone else that's moving side by side this mass, comma, will measure a mass that coincides, right, with the rest mass value. Those are the funny, consequences of that second postulate. The postulate of the second postulate, okay? The postulate that states that the velocity of the light is the same in any referential. So here is the behavior. Okay, some graphs here. I want to display that for you. You can plot that in Excel. You're going to get the same thing. We should have gamma here plotted. Let's see. Yeah, you don't have it. Yeah, we do have lens contraction here. Well, but we do have the relativistic mass plotted. Here you go. Here's the relative. This graph shows how the ratio of the magnitude of relativistic momentum to the magnitude of non-relativistic momentum. So what you see right here is actually the gamma factor, right? 1 divided by square root of 1 minus v squared over c squared. That's how the gamma factor behaves. At very low speed, you don't see any change whatsoever. This change only start to become apparent and measurable around, let's say, 0.3 c, 0.3 the speed of the light, okay, and diverges when the value for v becomes c. So, and it's the same thing for delta t, right? What you see here applies to delta t as well. So you don't see the clock in the spaceship seems to be flowing slower. So using your clock, if your clock measures 1 second, the other clock will be measuring less, right? And as the speed increases, the other clock seems to be slowing and seems to be slower and slower until it's nearby C. It just doesn't move at all. And that's what, again, is called the time dilation. Time dilation, time contraction, and increase of the mass. 3 different relativistic effects that people wouldn't believe at the time, but now this is a well-established theory. It's so well-established that we teach here in undergraduate school. Okay, it's 11:05 right now. Any questions about that? Don't forget, I'm going to be uploading 2 notes now. Okay, the other note became so heavy, so long that it start to give me troubles, right? So look for P07 notes.docx and P07 notes 1.doc. So break from 11:05 to 11:20 a.m. So when we are back, we look at this other section of this chapter, okay? I'll see you shortly in 15 minutes. Okay, so let's share the screen here. What I'm going to do here, that's the chapter on special relativity. You have, all those odd results just because of the postulates of special relativity. We covered 28.1, we covered 28.2, we covered 28.3, and we cover 28.4 and 5. what I'm gonna do, I want to cover this one, and I'm gonna skip this one because this one is a little bit too much, okay? What you have here is the equivalence of mass and energy. It's not just equivalence of mass of energy, but it is actually the relativistic energy. That's what we call the relativistic energy. Let's see what I found. This one here. Okay, so that's where the famous equation of Einstein comes to place. Okay. Okay. Total energy of an object. Let's take a look at that. Notes 1. Total energy of an object. I'm not going to do the derivation that you see right in here because it requires calculus and integral, differential and integral calculus, okay? This equation that you see right in here is the energy of an object that's moving. Okay? And in order to derive this energy, it requires, differential calculus. We cannot derive that in an algebraic format, unfortunately. And note that again, we have the gamma factor right in here. Okay? It's possible, okay? It is possible to derive the energy of a relativistic object by doing the following. I'm gonna just brush up how we go into the steps for deriving that equation. I'm not going to do the actual derivation. Okay. It's possible to derive the energy of a relativistic object by doing the following. 1. Using the equation for the network. Okay. The definition, right? The definition of network. So what's the definition of network? Definition that we saw of network in physics 6, right? Was work done by a net force is net force times delta x. Do you remember that? And don't forget that work has the dimension of energy. I'm gonna put work as the dimension of energy. Joules. Right in here is going to be, and let's not forget that the work kinetic energy theorem states that the work of the net force is equal to the final kinetic energy minus the initial kinetic energy. Well, when you do something like that, okay, and apply calculus to that, to this equation, you find that equation that is displayed there, okay? So using the definition of network, in the case, oh, it's not just that. The definition of network, 2 on the right, continue numbering, 3, that's terrible. That's set numbering value, let's see. Those are one of the bugs in Microsoft Word. I still haven't figured out how to fix that. Okay. In the equation, in the above equation, you use Now, in the above equation, you use the relativistic momentum for the net force, okay? And now what does it mean? So right in here, we end up using, delta P over delta T, like that, which is still equal to the difference of kinetic energy. And I'm even going to specify relativistic, okay? Not the regular delta P, but your relativistic one. After, after some computations, right? Derivation, after some derivation, we end up with the following formula. The relativistic energy is what? MC square. Again, it's not easy to get that because it requires a calculus, differential and integral calculus, divided by the square root of 1 minus v square over c square, like that. 1139. So going back here. Okay. So note C MC square right in here upstairs. Okay, for V, there is a very important consequence to this equation. That is a very important consequence to this equation. Okay. For V equal to 0, we get, if the mass is at rest, right, for V equal to 0, or if the mass is at rest, or if the mass is at rest, we get what? We get, this term goes away, and we are left with 1 only. Okay, this relationship is called the rest energy of the mass. This term is called the rest energy of the mass. Okay, compare this result to the classical, right? Classical means mechanical kinetic energy that we covered in physics 6. M, half of m v squared. Okay. If v is equal to 0, kinetic energy is equal to 0 as well. There is no rest energy whatsoever for the classical case, only for the relativistic case. And now, there's a very important consequence for this equation. right now, there's a relationship between mass and energy. So it's not that mass is conserved. It's not just mass is conserved. It's mass and energy are conserved. If something is losing energy, it's also losing mass. In the case of the sun, for instance, the sun is irradiating some of its energy through electromagnetic waves. It's losing energy by electromagnetic wave irradiation. What does it mean? It means that it's losing some of its mass as well. But there is even more important consequences to that. This equation shows to us that we can get a huge amount of energy from a rest mass if somehow you manage to convert this mass into energy. Notice that C is already a large number. C squared is even a larger number. So that's the principle of the atomic bomb, right? You have that mass of plutonium or uranium that you convert that mass into energy, into an explosion that radiates in the electromagnetic spectrum, in gamma rays, X-rays, and so on. So that's the start of the atomic bomb. Einstein, he derived this equation, and he left Nazi Germany because he was being persecuted by the Nazi party there in Germany, and he managed to immigrate to the United States. At that time, the scientists want to look at his equations, and they discovered that they could build a bomb that would release an enormous amount of energy. And some of Einstein's colleagues invited him to write a letter to the president of the United States to start a project to build an atomic bomb to defeat the Nazi. So he did write that letter. And on the top of that, Einstein also and then when the project Manhattan was approved, right? The project that built the atomic bomb was approved. Now Einstein applied for a security clearance to work in that project, but his security clearance was denied. He was the one who started everything, and yet he was denied the opportunity to work on the consequences of his own original work, which was the Manhattan Project that built the atomic bomb. Okay, it's a very nice story. There is a TV series about Einstein's life called Genius, and they go through this whole story in which Einstein applied for a security clearance to work in the Manhattan Project, but was denied, right? And later on, Vannevar Bush, who used to work in the federal government, approached Einstein to asking him to help with some problems related to the Manhattan Project. It shows, of course, problems that would result in material that was not classified. That's what happened. Okay. So at the end, Einstein did some work in the Manhattan Project, yes, but only in that work that didn't require any secret clearance whatsoever. Other people got security clearance, and they worked on this project, like Richard Feynman did that, Enrico Fermi, and many other, Robert Oppenheimer too, which later on was persecuted, not prosecuted, but persecuted, right? For his alleged communist ties. And it's a really nice story, okay? So here you go, again, compare the kinetic energy to this relation here. According to the classical theory, an object at rest has no kinetic energy whatsoever, has no energy whatsoever, and yet, according to relativity, an object at rest does have some energy, and it has lots of energy that's given by the mass of the object times c squared. We can even come up with the energy, for instance, of 1 kilogram object. Let's do that, just for the sake of here. E equal to m. Don't forget, m is the rest mass. Okay, C is equal to 300,000 kilometers per second, which is 300 million meters per second square. And let's see how much energy does how much rest energy does 1 kilogram mass has? MC, E is the energy, M is the mass, kilogram. Okay, now we have to square this guy. Okay, expand and simplify. That's the rest energy of 1 kilogram. Oh, don't forget this one is what? This one is joules. Can put that J here. No, user defined. Good. That's the amount of energy that 1 kilogram mass has. In reality, what you see here is the energy due to the atoms, due to the nucleus of an atom. Okay, and how can we get? How can you find out how big this thing is? Okay, think about that. You know, in order for you to understand the magnitude of this value, okay? So let's write it down. A 1 kilogram, a 1 kilogram mass has a rest energy of. I'm going to copy that and paste it here. I'm going to 10 to the 16 joules, right? How does it compare to the energy we use at home during 1 month, right? During 1 month, how does it compare? Okay, a regular house, on the average, a regular house on the average uses 300 kilowatt hour of energy, not power, but energy. Watt is power, right? But when watt is multiplied by a unit of time, it becomes energy. How much this and how many days would this amount of energy be able to supply for a regular household, right? Let's do the math. So here we go. First, we have to change 1 kilowatt hour to joules. Kilowatt hour. Okay, kilowatt hour is nothing but a kilowatt multiplied by hour, right? Kilowatt is also 1,000 joules per second. Okay, 1,000, not 100. Yep. Substitute right in here. And 1 hour is 3,600 seconds. 3,600 seconds, like that. I gotta do like that. Yeah, better. Okay, now look here. 1 kilowatt is 3,600,000 joules. But just 1 kilowatt, right? What about 300 kilowatts? I'm gonna write it down here. 300 kilowatt hour is going to be this many joules, okay? A 1,000, a million, a billion gigajoules. 1.08 gigajoule. 1.08. Let's see. 10 to the 9 is joules is 1 gigajoules. Kilo, mega, giga, right? Let's see if I can substitute that here. I can't. Let's see. I'm going to count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So is that 1.08 gigajoules? 1.08 gigajoules, which is 10, right? Let's see if it, oh, I didn't multiply by 300, right? 1 kilowatt. Ah, no, I did multiply. Yeah, I did multiply. But the other one, according to the energy of 1 kilogram mass, we don't have 10 to the 9, we have 10 to the 16, right? So here you go, energy of a 1 kilogram mass is 9 times 10 to the 16 joules. For how many months can we supply this household, right? All you have to do is to divide, that's the amount of energy for 1 month of a regular household, and that would be, let's see how many months we're going to get. Expand. Wow. So we are talking about, 10 to the 7 months. We're talking about 83 million months. Divide that by 12, and then you get the number of years that you would be able to supply just with the rest energy of a 1 kilogram mass. Calculate. That would be 6.9 millions of years. That's how much energy do we have? How much rest energy we have now? 1 kilogram mass. Okay. 1143 here. And that's what else can we do? The kinetic energy. Okay. The kinetic, here's the equation for the kinetic, the relativistic kinetic energy, right? It's the equation for the relativistic kinetic energy. If we go back to this equation here, okay? The work done by the net force, right? And the work done by the net force is going to be, you go, this much here. But now we do know that the kinetic energy at rest is going to be mc squared, right? The energy at rest is going to be mc squared, and then we can rewrite our energy, the energy, even in the book. Did you notice what I did here? I just used the work kinetic energy theorem here. Work of the net force is final kinetic energy minus initial kinetic energy. The initial kinetic energy would be the energy, the kinetic energy of a rest mass, right? But when the mass velocity of the mass is 0, the energy would be mc squared. That's what we did here. And let's see, let me get that side by side here. Let's see. Yeah, I'm going to do here. Here's the relation, right? all I have to do now is to solve for the final kinetic energy. Oh, it's not minus, right? It's plus, it's minus, yeah. Here. The final kinetic energy ends up being, you know, E minus E naught, okay? Which is mc squared over 1 square root one minus v squared over c squared, and E naught would be mc squared. Okay, and that's what they did here. Oops. And then we're putting the mc squared in evidence. Comes 1 here. That's what we have here in your. And one more thing that we can do. One more thing that we can do. What we have here, you know, how here can we here write, right, the ratio for very slow speed? I mean, by very low, I mean v much less than c. Okay? We do that, and your book did that by using the binomial theorem, binomial expansion. I did something similar before, okay? So in math, we can come up with an approximation for this ratio here, just by using this binomial approximation. That's going to be, you know, this value here, 1, oops, 1, you know, the power of this whole term, that is half. I'm going to sum up half. No, it's not my plus. It's, the power is going to be plus minus half, okay, times this term that you see right in here, right? Let me put another step here so you understand what's happening better. The square root that you see here is in reality this parenthesis that you see raised to the power half, right? Raised to the power half. And now I can eliminate the square root. And then we can put this term on the top. In order to do that, we have to change the sign, okay? And that's where the minus half comes from. And then we're going to have this term here, minus. But then you can have other terms as well. Okay, I'm just going to write down the way your book did. B squared over C squared. And then we have another square here. Okay, don't forget. And by the way, that should be a minus here. Here, the power is 1, right? This is a Taylor expansion. 1, 2, 3. Look what's happening here. If we keep just up to the first order term, this complicated ratio becomes something much simpler. A ratio that we can hardly observe, right? The minus here cancel out with this minus. The one we no longer need to write. And I remember I'm making an approximation because V over C is usually very small. V squared over C squared is also going to be very small. And this time it's going to be even smaller. So it's going to be a fourth power. So that can be neglected completely. Why are we doing that? We're doing that for V much less than C, okay? For V much less than C, this ratio is approximately that. Now, plugging in right here for my final kinetic energy, what do we get? We get something that reduces to the kinetic energy. And by the way, that's an approximation again, not an equality. See, let's see. This one cancel out with this one, right? And we gotta put an equal sign here. The C square cancels out with the C square. And we are left with the equation that you already know from physics 06, half mv squared. So what does it mean? What does it mean? It means that the equation for the relativistic kinetic energy reduces to the classical kinetic energy for V much less than C. Okay? Which give us confidence. This gives us confidence. This gives us confidence that the theory of relativity predicts. This gives us confidence that Newtonian theory is a consequence of the more genetic special relativity. Okay. That's what it means. Going to, and that's what your book is explaining as well. Okay, and it's 11:55 right now. And I'm going to prepare, we cover, which chapters we cover? I'm going to prepare before we finish the class, right? Let me write down here sections of chapter 28, 28.1, 28.2, 28.3, 28.1, 2, 3, 4, 5, and 6. Okay, 28.6. We're not going to do relativistic addition velocities. Okay. Any questions? Okay, so if you don't have any questions, we can finish now and we will meet again on Wednesday, right? So see you on Wednesday.